All right, so in this last section of Chapter 11, we're going to look at a chi-square test again. This is a chi-square test for independence, not goodness of fit. So even though they're both chi-square, you have to look for that. Is it a goodness of fit or is it independence? So this is looking for the independence. So we're going to be referring back to a contingency table that we used, I believe, back in Chapter 4. We first looked at contingency tables. We had an example that you may remember working where we were looking at different types of athletic wear, different brands, Under Armour, Nike, and Adidas, and then looking at the age of the consumer. So now we're going to look and see, is the age of consumer related to the brand that they buy, or is it not? So the null hypothesis is always that the variables are independent. In this case, we have two variables, age of the consumer and brand of the fitness wear. And the alternative is that they are dependent. Okay. So again, those contingency tables, and we'll look at one in just a minute if they're not ringing a bell for you, but they give us the probabilities that, let's say, a person is under 25 and buys Under Armour, or is under 25 or over 35 and buys Nike. So we'll have two different variables where we call them the X and the Y, and they are mutually exclusive events. So if you remember, this is when we're looking at the probabilities of unions and intersections and things like that. And each variable has to have two or more categories. So here's that contingency table that we've looked at, and we're going to continue with this one. So we see that we've grouped our consumers into two age groups, under 35, 35 or older, and then we have we've got 600 people here, and we've asked them two questions. What brand name did you buy, and how old are you? And so we've categorized those 600 people into these categories. So now we're going to see, are brand name and age independent, or are they dependent? Meaning, does the age of the consumer affect the brand name? Because obviously the brand name doesn't affect the age of the consumer. So this one can only go one way from a logical conclusion. But I want to point out, some of the studies that we look at, it could be dependent either way. And this test doesn't actually tell us which way the influence is going, just that they're dependent, that one depends on the other, but it doesn't tell us which one is causing the dependence. And this one, obviously the brand name doesn't affect how old you are, but how old you are could affect what brand that you buy. So this one can only be interpreted one way, but others, as you'll see in your homework, can be interpreted a different way. So first of all, we have to calculate the expected frequencies. So this is going to be the row total multiplied by the column total divided by the total sample size. Now, of course, we're going to do this in Excel, write some formulas, but let's just look at it from a manual perspective here so we can get an idea of the process, and then we'll jump over to Excel and do it. So when I look over here, I see, so we've totaled our rows. So out of the 600 people total that we surveyed, 396 were under 35, 204 were over 35, and then we have our column totals out of those 600 people. 228 bought Under Armour, 204 bought Nike, and 168 bought Adidas. So we can calculate our frequencies by multiplying, for example, what they call E11 would be your row and your column. So row 1, column 1 is this 174 right here where we're looking at, and we can say the expectation that someone is under 35 and buys Under Armour would be the row total of 396 multiplied by the column total of 228 divided by the total sample size of 600. So we would expect that approximately 140.48 people that are under 35 would buy Under Armour. And so then we can see for E12, that's row 1, column 2, we expect we expect 396 times 204 divided by 600, or 134.64 people to be under 35 and buy Nike. So we're going to calculate the expected frequency for each of these 6 squares here. So we'll end up with 6 expected frequencies, and we've done these by hand down here at the bottom, but of course we're going to do them in Excel in a moment. And then once we have all of our expected frequencies, we can calculate our chi-square test distribution. Now, again, this formula looks pretty nasty, but it is the observed value. So the O is the observed value in that row and column minus the expected value in that row and column squared divided by the expectation, and then you add them all up. Now the degrees of freedom are R1, so row minus 1 times column minus 1. So in this case we had 2 rows and 3 columns, so 2 minus 1 times 3 minus 1 gives us 1 times 2, or we have 2 degrees of freedom. Now we do have to keep in mind that each cell is expected to have 5 or more, and if it doesn't, then we'll have to combine like we did in the previous video. So let's go ahead and compute this manually, like I said, and then we'll do it in Excel in just a moment. So when we take our observed value minus the expected value squared, divided by the expected value for each of those 6 table values, and then we add them all up, we get a chi-square test statistic of 22.529. And then this is the number that we'll use in Excel to use our chi-square distribution right tail formula to calculate the p-value and see if it's less than 0.05. So let's jump over to Excel and actually do this one in Excel. Now, I mentioned earlier that Chapter 11 doesn't have a data file, but I decided to go ahead and make one. So you do have a data file now, and it will have this data in it here in this sheet that we'll title, I don't know, something. I'll decide in a moment. So this is just the data table that was already given to us, and I just went ahead and put it in Excel. Now notice I've substituted the names for B1, B2, B3, A1, A2. You could leave them as names if you wanted to, if that's helpful for you. First thing we need to go through is calculate all of our column and row totals. So I'm going to calculate my column total, and then I'm going to calculate my row total. I'm just using that sum formula, and then I'm going to drag that down, and so they all equal 600. So now I'm going to basically repeat this problem with the expected value. So I'm going to just copy this, and I'm going to place it over here in G, and then I'm going to delete that data, and this is where I'm going to put my expected values. So my expected value, remember for here for 1, 1 is going to be equal to the row 1, and it doesn't matter what order you multiply, row 1 times column 1 divided by my grand total of 600, my total sample size. So I can, if I make E5 an absolute value, I can drag this down. Oh. So I have E4 times B, that should be times B5. So you gotta watch it. You can't just drag completely. I'm gonna do some dragging here, but then we're gonna go back and edit it, right? So then this one is going to be E3, yeah, times C5 divided by 600, and that's correct. And so then this one is going to be E4 times, I need to open my parentheses, E4, goodness, I'll get it in a minute, times C5 divided by 600. Yep. And then this one, we'll just delete it and start over, is going to be E3. Oh, I clicked the wrong one. Times D5 divided by 600. I did leave out my parentheses, but it still works because the order of operations still applies. And then last one is going to be E4 times D5 divided by, again, my grand total of 600. So now I have all of my expected values here. And if I wanted to go through and calculate the differences, I can, or I can just kind of do that all at one time in my test. So real quickly before I get to that, I do want to calculate my degrees of freedom. Remember, my degrees of freedom are the number of rows. So I have 2 rows minus 1 times the number of columns. I have 3 columns minus 1. Again, put my enter sign. Yes. So I have 2 degrees of freedom. I just wanted to go ahead and have that there. All right. So then my chi-square test statistic is going to be equal to, okay, this is going to get a little gnarly here. It's going to be equal to, we're going to have 6 because we have 6 table values. We're going to have 6 of these terms, okay? So it is the observed value minus the expected value squared divided by the expected value. Then I'm going to do that for the next one. So again, the observed value, I open my parentheses, the observed value minus the expected value squared, I really think I need to put that in parentheses too, divided by the expected value. Ooh, and make sure that you get all your expected values in there correctly, because see, you can see how it's going to be super easy to accidentally click on the wrong one, and then you've calculated like all the wrong things. So make sure that you get all, you're very, very careful about this. All right, so let's do now the third one. So I've got my observed value minus the expected value squared divided by the expected value. So I've done the top row now, so I'm going to go to the bottom row. I've got my observed value minus the expected value squared divided by the expected value. I'm going to do it the 5th time. I've got now my observed value minus the expected value squared divided by the expected value. Oh, I think I missed a parentheses there. Oh, see? And it's really easy to accidentally... Okay. Yes, I know I'm missing a parentheses. I want that to be... See, if you accidentally click on the wrong thing, then Excel gets all kinds of angry at you. I was going to say, I felt like I accidentally forgot to close a parentheses. Okay. So I've got C4 minus I4 divided by I4. Okay. Somehow, see if you accidentally click off. Plus, now, again, last one. Observed value minus expected value squared divided by expected value. Okay, so let's check our answer. And we get 22.52907. So that is our chi-squared value here. Now, of course, we're going to plug this in now to our Excel to determine the p-value. So I'm going to use the same formula that I did before. So it's the chi-square distribution right tail. This is a right tail test. Now the first thing it asks me for is the test statistic, which is x, the value we just calculated, and then degrees of freedom. Don't forget that we just calculated as well. So now I can see, ooh, the p-value is very, 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 very small. So it is most definitely less than 0.05. It's even much less than 0.01. So we can say definitely that age and brand name are not independent. We are rejecting the null hypothesis to say that they are independent. We can definitely say that age and brand are are dependent. We're not accepting the alternative, but we are rejecting the null. Now, again, as I spoke of before, in this situation, it only makes sense to draw the conclusion that age is affecting brand name, because it doesn't make any sense to say that the brand name affects your age. But in other scenarios, as you'll see in your homework, it could go either way, right? It could be that you can't really determine in what direction the dependency is working. And the chi-square test doesn't, the independence test doesn't tell us what is influencing what. It just tells us that they are dependent or independent. So be very careful when you're drawing your conclusions.